look at aliphatic CH activation, quite generally, not all of those three mechanisms are important. I'll give you first a bit of background, maybe you think which ones work, which ones may not work. So, why do we want to have only active CH loops being activated? So I think there's perhaps two major driving forces to get into that field. One is the fact that we can valorize very simple raw materials. So if we generate, if we dig in fossil fuels, what comes out is basically unsubstituted alkanes, maybe branched alkanes, but it's a set of alkanes that we have at disposal. Why do we want to functionalize them? On one hand side, we want to valorize them, we want to add value, because the alkanes themselves are very inert. So we use them as very inert solvents, they are not reacting, that's the general perception. It would be nice if we get systems that can react and can add functional groups, and then we can use them for synthesis. And the second part, of course, is that at the moment we make very poor use of these fossil fuels. You know, about 10 to 20% of the CO2 emission comes from flaring, just from the gas components of fossil fuels sources that we can't transport. So we have two types of fossil fuels. One is the gases, the others will be the liquids. Now in most drilling stations we have a mix of those two. But the gases are not potent enough, so it's not worthwhile to construct pipelines all through the countryside to utilize those gases instead of natural gas. There are places where natural gas is the most prevalent part of the fossil fuel, and that's where we then get gas pipelines that travel all over. So for example, in, I don't know how this is here, in Europe, most of the natural gas comes from Russia. So there's huge pipelines coming from Russia to the west. But many of the drilling stations, for example, especially in the US and in Canada, they have a mix of gases and liquid components, but the gas components are too low. So what do you do with them? At the moment, nothing. At the moment, they just burn. Because you cannot saturate the atmosphere with methane and propane and butane. So what's being done is the gas components are separated from the liquids and they burn. Simply transformed to CO2. So that's extremely poor use. And it's environmentally extremely damaging. Yes, there's 10-20% of CO2 annually produced through this flaring. So having something that can make these gases valuable rather than just exhausting, combustible, would be highly desirable. And the demand is immense. So this is so much gas that it's just flared. So there's one huge energy component if you like, sustainability and having fossil fuels utilized more rationally, more responsibly. Then the other part is, of course, synthetic in nature. If we can have a very complex molecule and we can selectively address one or the other CH bonds, we can start building up molecules much more sustainably than what we do now with lots of functional group transformations here, there, and everywhere, and taking steps to synthesize natural product. If we can address the single CH bond selectively, we have totally new perspectives. So I think these are the two major drivers that aim at looking how we can functionalize alkyl CH bonds. At the moment, we have processes that can do this, that can functionalize alkanes. One is a very high energy consuming and very unselective process, that's the fission process and steam reforming, where we use carbon monoxide and dihydrogen from steam reforming, and over heterogeneous catalysts we form a range of hydrocarbons, alcohols, aldehydes, And then we do large-scale separations, so we generate basically from alkanes, we first generate carbon monoxide and dihydrogen via one catalyst, then by another catalyst we make the hydrocarbons and alcohols. But you see the issue here, energetically this drives you nuts. First you need 700 degrees and the ruthenium catalyst to make out of alkanes, to disassemble the whole alkane in its intrinsic components, carbons and hydrogens, and then we use some iron and another nickel or ruthenium complex, and again 700 degrees and pressure to make the alcohols. So a huge investment to go from hydrocarbons by steeping forming fish drops to alcohols. And then you have a mix. It's nothing selected. So you have like 700 products, and of course you can separate them at huge efforts. But it works. That's how we get at the moment all our functionalized molecules. We get this from those processes. The other thing would be hydrocarbon cracking. So again, by high temperatures on a heterogeneous support, we try to break up alkanes and get alkenes. Maybe if we have some oxygen in, we get as well alkenes. Again, selectivity is 0, so separations are a major point. And then the other alternative process, which is extremely elegant, works very well, is our enzymatic processes, but of course they're only working for a handful of selected substrates to give a handful of selected products, because enzymes are super selective. So if heterogeneous catalysts are not selective at all, the enzymes are the absolute contrary. A homogeneous catalysis can be bleaching. Homogeneous catalysis can be much more substrate tolerant than enzymes, but it can be more selective than heterogeneous processes. So enzymatic processes can, for example, with cyclotron P450, we can selectively oxidize a specific benzene to a phenol, as we use for phenylalanine to tyrosine transformation enzymes, dopamine synthesis. Methane monooxygenates, very relevant, can address methane, the ultimate alkane. Made selectively methane, a process that is still, we're all struggling to make synthetic. Well, we already talked about the bond dissociation. Why do we struggle to make methane and methanol from methane? Because we all face the problem that if we use oxidation sources, typically the substrate is less reactive than the product. So here we have 0 activity in the bonds. All 4 bonds are the same. In inducing a hydroxide, we start to polarize also the CH bonds, polarizing, making them more active. So, in fact, those CH bonds in this methanol molecule are more active than these ones. So, if we produce some methanol, any catalyst tends to be more active towards this molecule than to this one. So, it oxidizes this one further. We get formaldehyde, which is even more active to get formic acid. And formic acid we discussed, we manage easily to dehydrogenate or to oxidize formic acid, and you have done this in the lab. So here is the major issue in synthetic terms. So once we activate the methane, we tend to go straight to CO2. So we haven't really functionalized it, we just had to make a very complicated flaring process. What they're doing now, which is burning the methane to get CO2, we risk that we do the same in our fast. Maybe we have seen quickly the methanol before we say that it's just oxidized further. So that's one big issue, over-oxidation. And the other, of course, issue is how to make it the first step. If the CH bond is so inert, how can we make sure that the metal sees that CH bond and starts to function? The different aspects, the different methodologies, and different mechanisms how we can do this. If you consider what we discussed in the aromatic CH activation, you can basically start thinking of what are the lines you have to follow for aliphatic CH activation. We have looked at those three different mechanisms. Not all of them will work for aliphatic CH bonds. But I think based on your, I'd say, first year, second year undergraduate organic chemistry, you'll be able to tell me which of the three does not work with alkane CH activation. Remember what we need for sigma bond metathesis. We need a metal and a CH bond that can flip over. For a nucleophilic addition, we need an electron poor CH bond, ideally a relatively electron poor carbon. For electrophilic bond activation, we need an electron rich carbon. So that's the three concepts we have for bond activation. Can we do metathesis? So this is a plan forward. The other two? Can we do both? One is a bit difficult, more difficult than the other one. One is a bit more common than the other one. Nucleophilic is difficult and easy. Easier than the other. Okay? That's a 50-50. If I give you two, you're right. So that's an easy one. You can either be in favor of this proposal or against this proposal. Who is in favor of nucleophilic is easy, but it is possible. Who will be in favor of electrophilic is possible. So that's a near match, almost equal. Very low participation. Okay. Let me look at the functionalization in a stepwise manner, slightly from a different angle. I use slightly different vocabulary, but I do exactly the same. We substitute the CH for a CM, and then we have activated it. Yeah? So we do a substitution. So that would be a substitution nucleophilic, and that would be a substitution electrophilic. Now, I hope your organic knowledge starts helping. So, an aliphatic carbon to SN reactions or SE reactions. SN1, SN2, that's what the organic is breathing forever and always. And I hope you have been through that. So that's classic reactivity of aliphatic carbons. Electrophilic? No. Very difficult. We need unpolar reactions to get electrophilic reactions. So principally, for CH activation, if they're aliphatic, we have to eliminate more or less the concept of electrophoresis. Having said this, I'm talking here out of the past. I'm the old guy in here, so I tell you what others have done over the last 20 years. You're the future, so maybe go out and have a look, but there isn't really no electrophilic mass. You'll be the hero if you do. Of course, you cannot just write a research proposal, I do electrophilic CH actors. You need to have a plan. But if you have a plan, the world is yours. Totally new concept, nature, science. It may not be that easy, that's why you will go to nature science if you manage to have that. You need to be ambitious. Okay, so basically the two things we have the two mechanisms we should consider is nucleophilic oxidative addition of alkanes or sigma bond metathesis. That are the two major concepts we have to look and then try to tackle this problem of how to address it. So this is the sigma bond metathesis pathway. This is nothing new compared to the aromatic substitution, only that the carbon now is an alkyl carbon. But it has the same issues. We'd like to have here something that is fairly reactive. You get the side-on bonding first, like with dihydrogen. It slides over, you get the 4-member transition stage. It slides opposite. So you've transferred the hydrogen from the methyl to the R group, and you have activated the alkane. That's the classic. This has been demonstrated about 30 years ago in the late 80s for first time in a lutetium complex, in a lanthanide complex. What's the driver here? This lanthanide is actually undercoordinated. So you all know lanthanides like to have 7, 8, 9, up to 10 ligands around. So this one here is in fact very low coordinate with these eta 5 CP3 ligands, plus only 1 metal. So there's space, and if you keep that space empty, methane can coordinate, and you can get a metathesis, and this has been demonstrated with C13 labeled methane. So you replace eventually the normal methyl group on the lanthanide, eventually to only C13 label. So you can demonstrate that here you have activated methane.
Then is it possible to that hydrate transfer to metal and that RCS?
Is it possible to do the transfer with?
No, the product is MCH3 plus RH. So is it possible that it will form MH RCS?
That you call those two. So that you methylate the R. I don't think so. Maybe it is, maybe it's totally not favored. I have not seen any example that you can use alkanes as alkylanes. But that may be because we don't have enough of these examples.
No,
so
it is not observed, there is certain logic, so I want to know what is.
Yeah, so what you're I think the critical part here is that I'll draw you the intermediate slightly differently. So that's one. That would be the intermediate you'd like, because then you get the metal hydride, yeah? And that's the intermediate that is typically formed. And the issue here is that these are all, if you like, this one here is a 3 center 2 electron interaction
and this one here is the 3 center 2 electron interaction. So like, compare it with what you see, what you know, for example, from boranes. Which is the same, or for carbonyl dimers. Dicobalt octacarbonyl would have cobalt-carbonyl-cobalt interaction, where the bridging ligand has 2 electrons but bridges 2 metal centers. So here we draw 2 electrons too many in such a drawing. Because the boron is, in fact, it's a dimer of this compound. Yeah? So this is like a swipe wheel. It has only 2 electrons, but actually we draw 4. So there's a bit of a dichotomy or a bit of controversy in the drawing. But it's 2 center. It's 3 centers that bridge with 2 electrons. So this is very feasible for hydrides. It's much less common for alkyls. Hydrogens are doing this quite a bit because they have a spherical sigma orbit. With carbonyls, in carbonyls I think it's the pi orbitals that help to bridge this. But in alkenes, in alkyl complexes, you have a different you have a more polarized, a less available orbital that does this bridging. So we have much less of those bridging compounds in alkyl systems than in hydride systems. And that may explain you to some extent why it's always the hydrogen that bridges the 2 and not the carbon. You know, here we have the hydrogen bridging the 2 carbons. Here we have the methyl bridging the 2.
So you have to experiment to that orbital cell.
Yeah,
The ability of orbitals.
the ability of
Orbitals.
the availability of orbitals. Yes. Yes. I think that makes a difference, that it's typically the orientation that the hydrogen is swapping between carbon and carbon, and also the carbon is switching between hydrogen and carbon.
But for that aluminum complexes, AMC,
Yes.
there that methyl can.
True. For metal complexes, this becomes different, but I think at the metal, you have a much broader set of orbitals at the metal available to have different bonding. At the metal, yes. But here we talk about interactions. So the metal could do many things. You know, the metal can do this, and the metal can do this. No problem. But can the carbon do it? You know, can 2 carbons be involved adjacent in a 2 center 2 3 electron bond? I don't think so. You know, here 2 carbons have that 2 center, this 3 center 2 electron interaction. Here each carbon is separate. So each carbon gets fed by this and by that nucleus. So the metals and the hydrides can provide that electron density for a 3 center 2 electron bond. But 2 carbons adjacent, there's a deficiency of electron density. So I think that's what is not stable. So I think then you get into sigmatropic rearrangements. Maybe there it is. So no, even there you have extra electrons. So that's 4 electrons. So that would be a classic, but that's a 4-electron system. So I think in the electron deficient systems, this hasn't been seen for carbon. Now, because of the electron density at carbon, the carbons won't be adjacent in a two-electron interaction. They'll be opposite. And it's the orbital arrangement and the electron density at carbon. If you are, maybe the simplest explanation may be charges. That may help you. Why does it? So, you'd agree with that polarization? Yeah? And you'd agree with this polarization? Now, what's wrong with this one? And what's wrong? So here you have a nice equilibrium. So the positive charge is balanced by two negatives, the negative by two positives. So you have a fairly harmonic arrangement. Here you have so you have to
polarization is you can change time to time to explain different reaction.
we can
Carbon hydrogen polarization, sometimes we change that hydride will be shift so that H will be delta minus and carbon will be delta positive.
but we don't have this. Do you ever have a delta minus or did you have a carbon cation hydride? You know, if you manage this, yes, you can do it. But you need to make this one a hero if you can. No? So if you can do this, yes, then you enter. But I haven't seen this yet. Maybe now this becomes hydridic. But this is not aliphatic anymore. This is formaldehyde formic acid activation. So then we can start looking in hydrides. But then we lose all activity because here the reactivity goes the other way around. If we have delta plus metal, the delta plus metal sees much larger delta minuses. So for aliphatic CH activation, we can't look pole. We can't change the polarity at the CH. For functionalized, yes. So typically this works that way. Now what's wrong with that reaction? Nothing principally, but of course it's totally non-productive. It's proof of concept that we can activate methylene via metathesis reaction. No d electrons, no oxidative addition or nothing. It works. But we can't use it. And then I think so I'll have to use the board again because then it took a while, and only about 6-7 years ago this chemistry has moved to something that was useful. So how can we make now this metathesis to something that is profitable? It took a good few years to make this happen, but it was maybe you know the work of John Hartwig. He used this metathesis chemistry to to activate alkanes based on a rhodium catalyst. So he used a CP star rhodium benzene system, which can very easily lose its benzene at the 6-bound ligand. So in the presence of boranes, you get a displacement of the benzene by boranes. So the boranes oxidatively add, and you get a mixture of you forgive me, this is the same borane as everywhere. So we have this, even the rhodium 5 has an intermediate rhodium 3 with a sigma complex. And these react in alkanes and the alkane substitutes the borane as a sigma complex. Now this is bound for metathesis. Now you see we have the sigma bound thing and the alkyl complex, and that's exactly the pre-equilibrium that I had there. This one here, maybe you can see still, it's a bit blackish now, but this is exactly the same, where you have the alkane bound and you have the MR, which is here the M-boryl. And so that is set for a metathesis reaction. So we have four-membered intermediate transition state. And to flip it over, we have the new bond formed. And this new bond is, of course, very sterically shielded, not easily accessible. So getting we add in the alkane, we get this one out, we lose dihydrogen from here, replaced by the borane. Off it goes. You could draw for this dihydrogen loss in the presence of borane another sigma bond metathesis reaction, where the two hydrides, this one gets sigma bond have a second sigma bond metathesis which forms the dihydrogen, brings you back to this place here. And now we have a productive process. Now with this borane, this alkane, form a new functionalized product. And there are few key features. One is that if you look at this alkane and you wonder, say taken a longer chain alkane like pentane, what is the stability between this one here, where you have an internal carbon-hydrogen bond, sigma bond to the rhodium, versus an end-on bound? And I think it requires little imagination to see that the end-on bound is way more accessible than the internal stage. So what's the nice thing about this reaction? It's totally selective for terminal alkyl functionalization. So you get highly selective functionalization of the terminal bond. Works on relatively mild conditions, gives you one single product, so it's a very nice process that is really based on the single bond metathesis. So that's a very useful process. Again, it's a process.
So can you draw that the polarization of this catalysis?
Can you go?
Polarization. Delta plus delta borane.
In the borane?
This catalysis.
Here? Here? Yes. So here we're in a different mode, huh? Because I don't know. So I would have thought that the rhodium is more electron rich than the borane. I'd say the borane is intrinsically super electron deficient. So my view is that...
So that is rhodium.
Rhodium. What did I say? Did I say something else?
No, actually it's like ruthenium. So I said how the last one is the side.
So that's my silly handwriting. Yes. So this is rhodium 1. Yeah. Not ruthenium. Sorry. Yeah, this is a rhodium mediated process or catalyzed process. So I think in this case there's a rhodium minus and boron plus, and so you see it fits again, and that's why you don't have the hydrogen transfer to boron. If this would be the other way around, it's a useless process. So I think that was the key to bring that process somewhere. To have now not the metal as the Lewis acid and the carbon as the Lewis base, but having the boron. You know, what the others were showing in their initial paper was the lutetium was highly. And then the carbon that was originally on the metal is negative. And Hartwig, he didn't umpole the CH, he umpoled the metal side. So it's the borane, and then you have not the hydrogen that is transferred to the carbon. Yeah? So it has the umpoling to make it happen. But we cannot manipulate the alkane if we want to functionalize the alkane. Because otherwise it's already functionalized. But I think the ingenious part is that he changed the metal polarity. Because otherwise you're always stuck. You're making out of an alkane an alkane. Yeah. So that's the ingenious part here. I'm sure this can be done with others. You know, I'm sure if you think about, there's a good set of other fairly electron deficient compounds. Aluminum. Now, what is the key problem? The key problem is with aluminum that the product is not stable. You know, an organoaluminum thing, you have to immediately react that won't go anywhere. If you think this a bit further, you realize that maybe silanes. Silanes will be able to do this because the organosilane totally stable. And can be used for coupling. But they can't be used, so you know, the organoborons, they're nice because there's a bit more organic chemistry attached to organoboron compounds. Because we know from hydroboration of olefins, boron chemistry has been widely established. Now we know as well from hydrosilation we can go quite far. So maybe that's what it is. So very elegant work. Science of two, trail of 6-7 Jacks papers. So it is off to go do something nice. So that's the metathesis. The next one will be the oxidative addition, but I think since the bell will ring in 10 seconds or so, maybe better break up here. You had a question? No?